Welcome to part 4 of video series on relational databases Informal Introduction. In this part, we will be talking about fitting of various kinds of data into relational database tables. First of all, let's go back to our previously discussed problem of repeated values in one column. From previous parts, we already know that this is bad design for relational database, and this is because value in each column should be atomic, means that only one value should be stored in the column. And if you have something like comma-separated list, it's actually not good design solution. And this problem is illustrated here in this picture. And this problem is shown in pets column. So, for example, our employees may have pets, and we may want to store information about their pets. And obviously, one employee can have more than one pet. So in this case, it will be something like you currently see on the screen, something like comma-separated list of values. And somebody may have no pet at all. In this case, this value will be empty. So we already know that this is bad, and this was discussed before, but at that time we didn't actually suggest what would be right solution for this. Let's actually review this right solution. From previous examples, in particular, example with customer order and order item tables, you already can make guess actually what the solution could be. This is example of one-to-many relationship, and because one employer have more than one pet or potentially have more than one pet, and in this case we already know the right way to design such tables. We simply need to introduce another table. So we just removed pets column from employee table, and instead we created another table, employee pet. And now you see how data are very accurately structured here. And as always, you're already also familiar with this fact. If we introduce new table, we normally have some new power. So we normally have some ability to add new features. So for example, currently the table shown on the screen has exactly the same information as previously pets column had in employee table. But as it is now a new table, we already structured it. We put animal name into different columns, so it will be easy to query, either by animal type or by animal name. And we can have additional columns. For example, we can have another useful column, breed, to describe these pets. We can probably add a column age to store their age. However, at this point, you may say, hold on, age is actually a bad column because age is column where data will naturally expire next year. And you will be absolutely right. This is really not good. So I will remove this column. And instead, I will add proper column, which is year, meaning year of birth of this animal. So in this case, this data will never expire. So this is actually how our good design will look like. And the biggest benefit of this, we can now make very effective queries. We can query for particular animal type, for name, for particular breed, for the age, how old they are. We can group employees together by their pets. For example, dog owners come in one list and cat owners come in another list. So we can run so many different queries here. However, there is one interesting question. And this question actually taking us back to our previous example with bad design, where we had just pet column with comma-separated values. And the question is, can we run queries against this previous bad structure? So can we, if you had this previous structure, can we still run query for cat owners, for dog owners? Can we find employee by their pet name, if you know name of employee and name of the pet and want to know which employee owns this pet. So would we be able to run this query at all? And answer to this is not very straightforward because actually, yes, we can run such queries, and we will see examples of this in next screen. However, these queries will be both very bad for performance. These will not be performant queries, and they will return some kind of awkward results. So we cannot guarantee that results returned by these queries will be always correct. And now back to our working environment. So we need to create new table employee pet and fill it with data. I'm just showing you scripts for this. I will be not explaining them because you're already well familiar with both create table and insert statement. So this is all done. I already executed this script, so I already have table and I already have data in this table. Now let's run some queries against our new table. The first query I wanted to run, I wanted to have list all employees grouped by their pets. So I wanted actually list of cat owners separately, list of dog owners separately, and list of all other pet owners. So as always, I am writing select statement. And you can actually see how I'm writing this statement now. I am starting from the end. I'm first submitting table names, and later I will submit column names, which I'm taking from these tables. You can use this technique as well. It's very helpful if you want to use prompts from IntelliSense, because in order for IntelliSense to work properly, it needs to first know table names. So we will be selecting from employee table. I have suggestion for this employee. We need to join this table, and we will be joining with obviously employee pet table. And our join will be on ID column from employee table, which will be equal to employee ID column in employee pet table. Employee ID, this is all done. So now once I enter table names, it will be easier for me to enter column names because SQL Server knows what tables I am looking at. So I am typing first name, last name. And from employee table, I wanted to take name. I wanted to show name of their pet. So I could have just typed in name, but what I want to type first table name employee pet, and put dot, and then put name. Why I'm doing this? Because I suspect that column name could be also in employee table. It's not the case within this particular table, but normally table like employee may have column name. And this is just showing you technique how to resolve ambiguity when you have the same column name in two tables or in more than two tables which are within the same select statement. So if you have this situation, you can simply add prefix with table name and dot before your column. In this case, our product in SQL Server will know from which table to take it. And by the way, if you forget to do this and if you really have duplicated column names, it simply will not run this query. It will produce a syntax error, so it will guard you from situation where it doesn't know what table to take column from. And before pet name, I also wanted to show animal, which is in our situation is kind of animal. It is. I have these columns together. It all looks good, except that I didn't put the by statement yet. And I want to order by animal. As you remember, I wanted to have list of all different owners separately. So it looks like it's all done. So I go ahead and execute this statement. And yes, I have correct results. Now, as you see, they are grouped by animal. So first I have all cat owners, then I have all dog owners, and then I have rabbit owner. And also it illustrates that the same employee, in this case this lady, Sarah Bowden, could be mentioned more than once in this list. And this is correct because she is both cat owner and dog owner. So she first appears in the list as a cat owner and then as dog owner as well. So all done with this query. Our next query will be finding the owner of a particular pet. So suppose we found some dog which was lost, and we see tag of this dog, and we now learn that its name Leo. So we want to find who is the owner of this dog Leo. So again, we write a select statement. I already wrote the first portion of this statement here. We selecting from employee and employee pet table and joining them. We return only first and last name as result columns because we don't need to know anything else. We are just looking for an owner. And what is missing here is where clause. So we need to put where name equal Leo because we only wanted to get record for this particular pet. And probably we don't need order by clause here because we expect one record anyway. So all is done. We can go ahead and execute this statement. And here is our result. We found what we were looking for. The owner is John Clark. So lucky dog now found his owner. And one more comment here. If we want to ensure that we're only looking for dog with name Leo and not for any other pet with this name, which is also possible, we can type here and animal equal dog. As you remember, our table has all this information. This time we will have the same result because it was dog. It was one dog with this name anyway, but just to make sure that we are accurate, we probably also say that type of animal is dog. So all done with this query. You may wonder what would actually happen if we ignored all these design guidances and implemented our pets as just comma-separated list of values, like it was shown on previous screen where we have pets column in directly in employee table without creating separate table. You can already guess that it will be very difficult to run queries, but we were just trying with properly designed tables. But let's see actually how what they look like and what problems they would create. Anyway, it's very interesting just from point of view of studying this bad experience. Obviously, we will not advise you to follow it, but it will be interesting to see what happens in this case. So let's try to find owner of certain pet using pets column in employee table. I already went ahead and created this column and I filled it with the same data as were shown on previous slide. I'm not showing you scripts how to do this because it's bad design and I'm not supposed to give you examples of how to create this bad design. But I already created it for the purposes of illustration and trying to run query against such table. So I have select first name, last name from employee. And now, as you can guess, I need to put my where clause and we will be again looking for cat with certain name. This time we will look for cat with the name Lily. So I put where here. And as I cannot actually compare entire column to this name, I need to use function. Such function exists in SQL, call it char index. This function accepts first parameter is text string we are looking for. In our example, it will be Lily. And another item is column name where we'll be trying to find this string. And in our case, this will be pets. So what the statement is doing, it's actually, and I forgot to put more than 0. Our index function is finding position of the first substring within second string, which is column name, which is column. And if this substring is not found, the position returned will be 0. If it is found on any position, 1, 2, 3, on any other position, it will be more than 0. So we are looking for record where char index of Lily within pets column will be more than 0. And this is supposed to return us a record of the owner of this cat Lily. So we now go ahead and execute this statement. And it actually works good. It returned us a proper owner, Peter Ross. So what is actually wrong with this? You just saw it, it's working. First of all, what is wrong is this kind of query will be having very, very bad performance. You cannot see it right now because our table has only something like 5 or 6 records, and with this kind of tiny table, any query, even very poorly written query, will be executed almost immediately. But if we had 5 millions of records and we try to execute this query, we'll be running for very, very long time. And this is because we cannot use index on this pets column for this kind of search. We did not learn indexes yet. It will be explained in next parts of this series. But at this point, you can just believe me that we cannot apply index to the part of the column. If we were applying index, we need to compare entire column to certain value. And if we have index, our record could be found immediately. If we don't have index, we will need to scan entire table to find this record. It makes huge difference in terms of performance. But I'm actually at this point where we're working on database design, on how to actually lay out our tables and columns. I'm not very concerned with performance. I'm more concerned with the logic of this query. And it appears that it's also broken. The performance is very important, and I only mention this because it's a very obvious problem of this query, which is using this char index function. But I'm more concerned with a little bit different problem. Let's try to use this query to find our dog Leo like we did in our previous examples. In order to do this, I will simply copy and paste this query. So I will create another copy of this query, and this time I will be looking for Leo instead of Lily. Now I highlight it and execute it. And you can now see what happened. We have wrong results. We have 2 owners now. And we know actually there was only one owner of dog Leo. So what happened here could be very easy explained if we add its column. This is our wrong designed column, which actually made this problem. Try to execute the statement again. Now we have content of this pets column, and we understand what happened. We look at its substring Leo, and it did find one correct record, which is John Clark, who is owner of dog Leo. But it also found substring Leo here because it was cat Cleo, and you see this cat didn't even have name Leo, it was Cleo, but Leo is part of this name. So it did find one wrong owner, so it looks like it's not just slowly executing query, it's also incorrect query because it's returning wrong results. Of course, we can somehow improve it, we can somehow make it to look only between commas, and we can make it to look at some spaces as well. But in this case, as you may understand, it will be tremendously complex, so it will be very difficult to write this expression properly. And with proper design, with just using separate table, we don't have any problem at all. Our query is very straightforward, very simple, and it's performing perfectly. And now let's come back to another example we were also considering before. It was actually in one of previous parts. And this example was about storing hobbies of employees. And this is the same problem as we had before. We're trying to store comma-separated list in one column, and we already know that this is bad. But how would we implement it this time? As you may see, situation is a little bit different from previous example. Previous example was when we were storing pets for employees. A previous example was example of one-to-many relationship, because there was one employee and many pets which could belong to him or to her. Now, this time it's a little bit different, because one employee can have many hobbies. And also the same true for the other side of the table, because one hobby could be hobby of more than one employee. For example, in this table, we can see that 2 people play golf, 2 people play chess. So it's actually different kind of relationship. And this kind of relationship is known as many-to-many relationship, because many items could be on both sides of relationship. So how we implement this? We already know that having this hobbies column is bad, so we remove this column. Instead, we introduce table which store hobbies separately. This time, this table alone is not sufficient. We also need to introduce another table, which is currently shown on the right. And this table is known as connection table or link table. This table will link our two tables, employee and hobby, together. As you can see, it refers to both this table. It has employee ID and hobby ID. So if employee with certain ID has hobby with certain ID, this table will have record for this. So now we can see that this table points to both primary tables, and both employee ID and hobby ID are foreign keys in this table. And as always, you probably already used to this. We have some additional benefit when we introduce another table, and this benefit is illustrated by another column I added to this link table, and column called skill. So not only we can reflect the fact that a certain employee has certain hobby, but we can also reflect skill in this hobby. For example, in the scale from 1 to 5, we can actually store how skilled they are in this hobby, for example, in playing golf or in playing chess. And this is example of the fact that this link table is not necessarily purely link table. It could be serving both purposes. It could be link table, and also it could be storing some useful information as well, like illustrated in this example. So now we have three tables, and all three tables have different cardinalities, and all tables are totally independent on each other. So each table can have any number of records, and they are not actually tied to each other by how many records they have. And this is very flexible, very convenient, because anybody can have any number of hobbies or do not have any hobbies at all, and the same is true for the opposite side of the table. Now, interesting fact actually to note what currently would be primary key for this employee hobby table. We already know that primary key for employee table is its ID, and for hobby it's also ID for that table. But what would be primary key for employee hobby table? In this example, we are facing actually a case where we have so-called composite primary key. Composite primary key is a case where more than one column is within primary key. So neither employee ID or hobby ID alone will be primary key, but they will be primary key together, which means that their combination is always unique, and they always supposed to have some value. They are never empty. So this is example of composite primary key, and now you learn that it is also possible for primary key to consist of more than one column. Okay, I think this example is more or less clear. I am not going to provide some coding examples for this case because it would be very similar to what we had before. Our queries would be very similar. The only difference that now we need to connect three tables together, and you already know how to join more than one table in the same select statement. Let's talk about very common problem. We have objects which are very similar to each other, but little bit different. This is actually happening all the time, and when dealing with this, we are hitting some of the biggest restriction of relational database, which is handling data in tables, and tables are well defined. So if we define a table for our object, it expects that all objects stored in this table will be the same. But real life is a little bit more complex. Let's assume that we are running some kind of small shop, and we are selling different kind of products. We are selling dairy products, we are selling meat products, and also we sell batteries. Many shops which sell food also sell batteries for some miscellaneous purposes. And what these products or these items, what fields do they require? All our selling items require the same columns, which are price, name, barcode, weight, shelf number where this product is located, and some logical field taxable. Is it taxable item or is it tax-free item? So all our selling items will have this information regardless of their nature, because this applies to everything we sell in shop. However, there would be also some specific fields. For example, dairy products, in addition to all these fields, also need to store fat content and calcium. They need This milk product will normally want to see this information. Meat products have their specific fields. This is meat kind. Meat kind means what kind of meat. Is it pork? Is it beef? Is it veal? And what particular cut of this meat this item represents. And batteries certainly need to store voltage. How do we actually deal with this variety of products? They're almost the same because price, name, barcode, all this feels the same, but they're a little bit different. Well, as you probably already know from previous examples, when we have any difficulties, any challenges, we create more than one table. So let's do this in this example as well. In this case, we will create three separate tables. The first table will be for dairy products, second table for meat products, and the third table for battery. Now, if you look at column names in these tables, you see that they're almost the same. You see they have the same columns except of very last ones. So how would we deal with this variety of tables? And with dealing with all this series of tables, our main concern is always how do we run our typical queries. As you remember, database is all about running queries. And some queries are most important ones for our business. Some other queries are less important. So what do you think is the most important query, most frequently executed query in this situation? I think it would be a query which finds product by barcode. This is actually typical query when you go to check out. This is kind of query you may be facing almost every day in your real life. Whenever you are shopping in any grocery store, in any other kind of store, when you go to check out and you present your items for scanning, there is some system on the back. It's not visible to you, but it always exists because databases are very widely used. They are obviously used in all these supermarkets as well. So the typical query which you're actually causing when you come into checkout will be to find this item by barcode. Your cashier will scan barcode and this will go to some system, and system should identify price of this item and name of this item in order to print it on your receipt. So this is actually a query not only typical for database, this is query which you probably, as I already said, facing almost every day in your real life, even without realizing that you're facing it. So how would we implement this very important, very typical query in this database schema? Probably once we have barcode, we need to check this barcode against all tables, because when our system receives barcode, it doesn't know actually what this product is. It doesn't know is it dairy product, is it meat product, or is it battery. So it will first execute select statement in the form which is currently shown against dairy table, and it will try to find records with certain barcode. If it failed to find records there, it will probably go to next table, which is meat in this case, and then if it didn't find it there, it will try finally take it from battery table. So as you can see, we are now executing 3 queries instead of 1, which is already not looking good enough. There is some workaround around this, and this is actually trying to execute all 3 queries at once. And fortunately, SQL allows us to do this. Let me introduce you another statement. This is a select statement which has union clause. And this select statement connects different separate select statements. As you can see, I have 3 select statements, which are similar to the ones shown on the top, and I have union between them. It means that I'm requesting to create some kind of virtual table to execute select statement on all 3 tables and create some kind of virtual table which puts them together. So this statement in its presented form will work, but it will simply return everything which shop has. This is not our intention. We wanted to search for barcode. So in order to do this, we do another syntax addition to this statement. First, we need to enclose this series of union statements in parentheses. Then we put select star from at the top, because we're currently selecting from this virtual table. At the bottom, we see that we assign some name to this table. We call it a product. This is virtual table. It only exists in this query, but it has to have some name to work with this effectively. And at the very bottom, we put where clause, which is well known to us, where barcode equal to our value. So this way, it's a little bit better than previous example because we're actually executing one statement, well, one big statement, one combined statement, but we are getting only one check for barcode, so we're not checking it 3 times. But it's not ideal. First of all, the first thing you probably already noticed yourself, it's pretty complex. So it's very, very difficult to see, to read it, to understand it. But there is actually a bigger problem to this. And the biggest problem is not how complex the syntax is. The biggest problem is that we now developed some kind of dependency on 3 tables. And dependency was developed in our code. So our code is not very flexible now. So whatever code we have in our application, which is executing this statement, it should have knowledge about all these 3 tables. What it means from practical point of view, it means that if you want to introduce another table, for example, we started to produce some different kind of product. We now need to go to our code and update it because it doesn't know this table. So we need to add another table. Or the same would happen if we discontinued some product. Let's say that we are no longer selling batteries and we decided to drop this table. We deleted it from database. Now all code in our application will be failing because it will try to access table which doesn't exist and it will be cause an exception. So this is not good. So now every time we update anything in our products hierarchy, in the products we offer, we need to update all code which is working with this. This is not flexible. And the most disappointing fact is that we are doing it without any visible benefits. Because as you can see, all our 3 queries are actually working with the same columns. So they do not use any benefit of presence of this additional column. If you remember, the reason why we introduced these 3 tables was that we wanted to store some specific columns, which was fat, calcium, voltage, all these specific columns. And that was actually in order to address other parts of application, which may be not as important as this query we are looking at. We're currently looking at our most important query. This is where we need actually to get biggest performance. And we made some damage to this query because this query became now complex and dependent on our database configuration. So if previous design was not really good, then let's think what else could we do. Our next attempt would be to create just one big table which stores everything. And this table is currently shown on the screen. It's a very wide table. It has all mandatory columns, meaning all columns which all objects should have: price, name, barcode, weight, shelf number, and taxable. And it also has all additional columns gathered from different kind of objects. So for dairy products, it will have fat and calcium. For other products, it will have other columns. And now it has all of them together. So what could we say about this design approach? Well, first of all, there is one good thing about this. Good thing is that our main query, and if you remember, our main query was a query which was finding products by barcode, is currently working good. This is just simply one single select statement, no need to run different statements, and now we eliminated dependency on many tables. So now if we add additional line of products, our statement is the same. We don't need to change it because we just have one single table product which stores everything. So that was positive side, but there are many negative sides as well. First of all, you probably noticed that we introduced so-called sparsity into table. This means that not all cells are now filled with data, and some of them are always empty, not just temporary empty, they will be always empty. For example, for first 2 rows, which deal with dairy products with milk and cream, columns meat kind, cut, and voltage will be always empty because they're simply not applicable. And there are other empty cells as well. What could we say about sparsity? First of all, it's not following good relational design guidance because relational table is supposed to have all values filled. So the idea of good relational design, so either you have all values present or you do not have this column at all if it's not supposed to be there, if it's not supposed to have any value within this table. So currently we are violating this approach. Another thing, is it really acceptable? So in ideal world, for ideal design, this is not acceptable. In real life, sometimes it is acceptable. And in your practice, in your real business experience, you will see many tables with this problem with sparsity. They are pretty common for many databases. So they are somewhat acceptable if you apply the following rule. You need to ask yourself why this cell is empty. Is it empty because value is simply unknown? But it could be known, so it could be actually assigned to this particular object. Or is this value not making or that column is not making any sense at all, meaning that it's not even applicable to this object. In this case, sparsity is really a very bad thing. So example, when it's unknown would be, for example, this weight column. Let's say that we don't know weight for battery. It's actually quite possible battery do not always show their weight, but weight is making sense for battery. It does weigh something. It's actually a particular item. It's tangible item which does have some weight. So the fact that we do not know weight may be not very important for us because it's maybe not important what kind of weight this battery has, but at least it's making sense. But now is within this design you can introduce actually bigger problem. For example, by some mistake or oversight, you can assign voltage to the milk. Or, another example, you can assign fat to battery. But these are not acceptable cases. And these cases illustrate the case when value is not applicable. It's not simply unknown. It's not applicable. It's not making any sense. And this table not just looks ridiculous with these values. It's actually a problem that this table is not driving good application design. Somewhere at the beginning of this series, I told you that a perfectly designed database is normally making entire application, entire system perfectly designed. So it actually dictates how other parts of system will be designed. And one of the way how it would do it is a perfectly designed database will provide a high level of data integrity. Data integrity in general means that it's guarding you against making some mistakes in your data. So it would not allow you to put some wrong information into database. Data integrity is a big topic. It could be achieved by different means, but currently we are talking about one part of data integrity. We did allow to put wrong data, so we did allow to put voltage for milk or fat for battery. It means that if somebody is writing some user interface for the application and not giving proper documentation, they may be trying to provide some fields in user interface just to fill all columns in this table. So it's quite possible that they will provide some fields which are not making any sense. And you can argue that probably every prudent person will understand that voltage doesn't apply to milk and that fat doesn't apply to battery, so they wouldn't do this mistake. But this is only because my example is pretty explicit, it's pretty clear. And this is only clear in this example. Let's say you have other column names, something like production code. How do you know whether it's applicable to battery, whether it's applicable to milk? You will never know this, actually. So the conclusion here, this design is not actually, this table design is not driving good application design. And finally, correct design for this problem. So the best design would be to create separate product table, which will have only columns which are common for all of our products, price, name, etc. And then we create another table which is only having columns for dairy products, which is fat and calcium. And as you may now guess, we create another table which has only columns for meat products. And we have another table for battery, which is storing its unique column voltage. And now we have logical link between all these 4 tables. They are linked by their ID. The ID value in all 4 tables is the same. So if certain product has some ID in product table, and if it is dairy product, it will have record in dairy table with the same ID. So these 3 tables which were added to product table are known as extension tables. They extend their main table, which is product. They provide additional columns for this. And you may also pay some attention to how I named these extension tables. You see, I named them after their main table and added another word which explains the nature of this table. For example, for dairy, I named it product dairy, which means that it's extended product table for dairy products. So this design is pretty good and accurate. And one interesting note about these tables, if you look at ID column in our extension table, it's actually both primary key and foreign key. Sometimes it happens. It's primary key for this table because it's unique ID for the table and it always has value, but it's also foreign key with regards of product table because it's inherited from that table. Another note is that our most typical query now run perfectly. Our most typical query, if you remember, was to select product by barcode. But most of our typical queries which we'll have also will run very good. For example, if we want to select products within a certain price range, we can simply execute it against product table. Or if we want to find all products which are placed on certain shelf, we also run very easy query. And whenever we need columns from both tables or from all 3 or all 4 tables, we simply, as you may guess, make join for this. For example, if we want to know how price of dairy product depends on fat value, so in this case we need results which are showing both fat and price and probably name. We simply join product table with product dairy table by the column which you can guess is ID. And we eliminated sparsity from these tables. There is no sparsity. All cells will be filled with data because we do not provide actually any extra cells. And what is also important, we no longer provide option to store some awkward data combination, like it was shown in previous example, where we were able to store voltage for dairy products or fat for batteries. So good design has been achieved. This is end of part 4 of video series on relational databases Informal Introduction. In this part, we talked about fitting various kinds of data into database tables. This talk is not complete yet because we only looked at very simple structures, and next parts will be talking about fitting of more complex structures into database tables.